Hello everyone, I'm Si Yang from University of Southern California. Today I will introduce a 29 milliwatt, 26.88 GHz non-uniform subsampling receiver front-end, enabling spectral alias spreading. The presentation is organized as follows. The first part is the motivation of the research. Then I will introduce the proposed technique and circuit implementation. Next, the measured results will be provided to prove the effectiveness of this work. Finally, I will conclude my presentation. Let's start with the motivation part. To begin with my talk, let's first look at the conventional receiver architectures, heterodyne receiver, and subsampling receiver. The heterodyne receiver architecture alleviates the noise folding issue compared to the subsampling receiver. However, the I/O frequency of the mixer is high and consumes a lot of power, especially in the millimeter wave applications. Also, the clock tree distribution of the I/O becomes another issue due to the stringent requirement of the low jitter. To simplify the receiver design complexity and lower down the power consumption, the subsampling receiver is used as a mixerless receiver architecture to mitigate these issues. Although the frequency becomes lower, a low jitter subsampling clock is required. Furthermore, the analog bandpass filters are needed to reduce the destructive aliasing issue. Usually, these analog filters are off-chip and bulky to achieve sharp frequency response. As a result, the analog bandpass filters are the bottleneck of the high-performance on-chip subsampling receiver system. Since the bandpass filter is used to solve the aliasing issue, let's re-examine the reason of the aliasing issue in the subsampling technique. In the uniform subsampling receiver, the input is sampled by the clock with uniform sampling time instance. In the spectrum, a band-limited signal around the carrier frequency Fc will be down-converted to the baseband during the subsampling. Now, we consider the worst case of this uniform subsampling receiver. If there is a blocker at the alias band, for example, Fc plus Fs, here Fs is the sampling rate. The blocker will be down-converted to the baseband as well and added on top of the desired signal. Because the signal and blocker are down-converted with the same conversion gain, the signal is totally interfered by this blocker. To solve this aliasing issue, there are two conventional solutions. The first solution is to apply the analog bandpass filter with sharp frequency response to reject the blocker before the subsampling process. The bandpass filter with high order roll-off is difficult to implement on-chip. Another solution is increasing the sampling rate. In this time, the alias band becomes far away from the carrier frequency and there will be sufficient rejection with a relaxed bandpass filter. However, the power consumption is increased with a higher sampling rate. Here comes the question, is there any other way to solve the aliasing issue without these overheads? Since the total power is conservative during the sampling, we are trying to change the distribution of the alias after subsample. This concept is described as the spectral alias spreading, as shown in the figure. In this target spectrum, the conversion gain of the alias is reduced. Here, we define the alias rejection ratio as the amount of the down-converted alias in the baseband. In terms of the alias itself, it is rejected by a filter equivalently. Different from uniform subsampling clock, we intentionally give a periodic perturbation on top of a uniform sampling instance. Each perturbation is confined in one sampling period so that every sampling instant can be always earlier than the next one. The input waveform is sampled by this clock with non-uniform sampling instance. The Fourier transform of this non-uniform sampling instance is similar to the early mentioned target spectrum. The down-converted undesired blocker gets rejected during the non-uniform subsampling process, and the aliasing issue is solved. The alias gets rejected at the alias band, but becomes smaller chunks and spread out. In this alias spreading phenomenon, the small chunks can be further removed by the digital filter in the post-processing. Compared to the conventional solution of aliasing issue, the requirement of the analog bandpass filter can be relaxed without increasing sampling rate. Because our solution is embedded in the sampling process, it is compatible with other alias rejection techniques. In our proposed non-uniform subsampling receiver architecture, a non-uniform clock replaces the uniform clock to finish the subsampling process. In this way, we take the advantages of the subsampling receiver architecture and relax the analog bandpass filter requirement. Although there are additional blocks to control the non-uniform clock sampling instance, the power and cost are much smaller compared to the mixer in the heterodyne receiver architecture. Moreover, the non-uniform clock pattern is reconfigurable and can be optimized to reject a certain alias. This non-uniform subsampling receiver can also be configured in the uniform subsampling mode just by setting 0 perturbation for each sampling instant. Unfortunately, more interferences will be induced during the non-uniform subsampling process. Because these interferences are out of band, they can be removed by the non-uniform DSP technique after post-processing. Also, since these induced interferences are relatively small, the cost of the non-uniform DSP is low. Then the next question is how to generate this non-uniform clock. Here shows the procedure to generate the NUSS pattern. In the design of NUSS pattern, the expression of the alias rejection ratio is used as a cost function for the optimization purpose. In the expression of ARR, the L represents the periodicity of the non-uniform clock. Vector S is the variable to be optimized. The S element of vector S is S of I, which is the normalized phase shift of S sampling instant. Our target is to find this vector S to minimize the absolute value of this expression. First, the normalized phase shift S of I should be integer from 0 to Fc over Fs. In this way, the periodic perturbation is the integer multiple of a unit time grid, Tg. This time grid, Tg, is the reciprocal of the carrier frequency, which makes sure that the signal can be directly down-converted to DC without any conversion loss. Then, the S of I should be uniformly distributed within one sampling period to reject aliases. As shown in the histogram, 0, 1, 2 until Fc over Fs minus 1 should occur with the same number of times. This constraint is called uniformly distributed perturbation. After applying this constraint, we should also consider the blocker location, KFS, which has been included in the expression of ARR. Finally, different optimization methods, for example, gradient descent method, can be used to generate the non-uniform clock pattern. One of those prepared clock patterns is utilized according to the specific application. To verify the proposed technique, we implement the system and do the measurement. The non-uniform subsampling receiver consists of input buffers, 4 time-interleaved sampling networks, and output buffers for testing purpose. The input buffer is used for input matching and followed by 2 source follower buffers. These source follower buffers reduce the sampling-induced noise coupling between the time-interleaved sampling networks. The non-uniform clocks are generated externally and buffered on-chip to drive the sampling network of each channel. The master-slave two-stage sampling network is implemented in each channel. To ensure sufficient settling accuracy, the tracking bandwidth of the master sampling network is designed to be 33 GHz. The slave sampling network is designed to reduce the output settling error. A bootstrap switch in both the master and slave samplers improves linearity. Now, I will go through the non-uniform subsample clock scheme. The proposed non-uniform clock is implemented using 4 time-interleaved channels to get sufficient tracking time. The unit time grid is 1/Fc, which is around 37 picoseconds. The non-uniform periodic phase shift is embedded into the clock. In our prototype, the normalized phase shift, Si, is within 0 to 7. The periodicity of the non-uniform clock pattern is 16, so the sampling instant of each channel is repeated every 4 samples. This clock pattern is generated using the aforementioned constraint and optimization methods. Our prototype is fabricated in TSMC 28nm process. The total coil area of the NUSS receiver without output buffer is 0.15 mm². Here shows the measurement setup of the NUSS receiver. On the input side, a single tone F1 is generated at baseband and up-converted to the millimeter wave band. The mixing frequency F2 is from another signal generator. We have 2 single tone with same magnitude from mixer output, which are F2 plus minus F1. One of these 2 tones is viewed as the desired signal, and the other one becomes undesired blocker. These 2 tones are sent into the chip through the power splitter and the probe. On the output side, the non-uniform samples come into the differential to single-end active probes and captured by the oscilloscope. The digitized non-uniform output from oscilloscope is reconstructed as the uniform samples using non-uniform DSP, that is NUDSP. The NUDSP also removes the other small jumps induced by the non-uniform subsampling. The non-uniform clock pattern is prepared before the measurement and loaded into the chip through the EDAP-G. The phase detector PD is implemented on-chip to check the clock skew between different channels, and the laptop is used to control the function of the chip. This figure shows the measured spectrum of the chip output after post-processing. The signal is 100 MHz single sideband, and the spectrum is shown within the signal band. In the uniform subsampling case, the magnitude of the folded blocker is the same as the magnitude of the down-converted signal. In the non-uniform subsampling test, the folded blocker is rejected over 30 dB thanks to the spectral alias spreading. Later, we fix the signal frequency and sweep the blocker location in different regions around the carrier frequency. In this way, we get the measured frequency response of different non-uniform clock. The non-uniform clock S1 is optimized for the region around 6 fs, and in this region, the blue curve shows a deeper notch. Similarly, the non-uniform clock S2 is optimized for the region around 7 fs, and in that region, the yellow curve shows a deeper notch. In addition, the comparison between the uniform and non-uniform subsampling of modulated signal is shown here. We replace the single-tone signal with a 100 MHz single-carrier 64-QAM signal. The power of the input blocker and the signal are the same. In the spectrum of the uniform subsampling result, there is an in-band folded blocker and the signal cannot be reconstructed. After applying the non-uniform subsampling technique, the folded blocker is overwhelmed by the signal, and the reconstructed signal achieves -25 dB EVM. This table shows a comparison to the state-of-the-art subsampling receivers. The proposed architecture is designed for the millimeter wave applications, and our core chip area is also smaller compared to the other ones. Our proposed non-uniform subsampling methods is used to reject alias and achieves up to 33 dB alias rejection without any analog filter. Here comes the conclusion. The proposed non-uniform subsampling is the first sampling network embedded alias rejection technique and can be combined with analog anti-aliasing filters to achieve an even higher alias rejection ratio. A millimeter wave receiver front end without analog anti-aliasing filter is demonstrated, achieving over 30 dB alias rejection due to the spectral alias spreading. Compared to the other state-of-the-art subsampling receivers, the NUSS receiver achieves 200 MHz instantaneous bandwidth with 0.15 mm² core area. We would like to thank all sponsors and the people we have interacted with. Thanks for your attention.